Hi friends, welcome back to engineering tutorial. Today we are going to discuss about full wave rectifier. Now you remember that in my earlier video I discussed with you all about half wave rectifier. Its a basic construction principle, the components used, the working of the half wave rectifier, and also about its advantages and disadvantages. Now one of the disadvantages of the half wave rectifier is that it utilizes only one half cycle of the signal waveform, that is the positive half cycle. It's activated only during the positive half cycle, during which conduction of current takes place, while it is off during the negative half cycle. Now this disadvantage of half wave rectifier is overcome by the full wave rectifier. So a full wave rectifier is an electronic circuit which conducts during both the half cycles of the signal waveform, that is during the positive and the negative half cycle. So it utilizes both positive and negative half cycle, and current conduction takes place during both the half cycle or the complete or full signal waveform. That's why it is called as a full wave rectifier. Conversion of AC into DC takes place during both the half cycles. Now this is achieved by the use of two diodes as opposed to the one diode which is used in half wave rectifier. These two diodes are made to work alternatively, to work during both the positive and negative half cycles. Now two most commonly used circuits to achieve full wave rectification are the center tap full wave rectifier and the full wave bridge rectifier. Now we are going to discuss these two separately in detail. Now let us first discuss about the center tapped full wave rectifier. This is the circuit diagram of the center tap full wave rectifier. Now, as you see, similar to the half wave rectifier, it also has AC supply, which is the fundamental requirement, which is to be converted into DC. This is connected to the two ends of the primary winding of the step up or step down transformer as per the requirements. Now two diodes are used here, D1 and D2. The p-type ends of the two diodes are connected to the two ends of the secondary winding of the transformer, while the n-type ends are shorted together. Now a load resistance RL is used, whose one end is connected to the center tap secondary winding, while the other end is connected to the shorted n-type ends of both the diodes. So this is the basic design or layout of a center tap full wave rectifier. Now we are going to discuss about the working, the operation of a center tap full wave rectifier. So we are going to divide the operation in terms of two half cycles. Now during the positive half cycle of the input, that is positive waveform followed by the negative waveform, the ends A and B of the secondary winding of the transformer attain positive and negative polarities respectively. So because of this, the diode D1 with its p-type end connected to the positive terminal is forward biased and gets short circuited and is activated, while the diode D2, which has its p-type end connected to the negative terminal as B attains negative polarity, gets open circuited due to reverse bias and deactivated. So as a result of this, diode D1 gets short circuited and conducts the current from the positive terminal through the diode following this direction through the load resistance from the positive to the negative polarity. The load resistance, this end of the load resistance attains positive polarity as it is connected to the positive polarity end of the secondary winding, while this attains negative as it is connected to the negative center tap point on the secondary winding. The voltage across the primary winding divides itself equally among OA and OB at the center tap point on the secondary. Positive, here one voltage, positive negative polarity, here another equal voltage, positive negative polarity. So the current flows from positive to negative, and hence we get a DC output. Now during the negative half cycle, the opposite happens. The end A of the secondary winding becomes negative, while the end B becomes positive. Same thing happens. The voltage at the primary winding, the reverse voltage at the primary winding divides itself equally at the center tap point. Negative positive voltage here, or minus plus voltage Vm here. It divides itself equally. So as a result of that, the p-type end of D1 being connected to the negative polarity end, it becomes reverse biased and is open circuited, while diode D2 with its p-type end connected to the positive terminal is forward biased and is short circuited. So in this case too, current flows from the positive terminal or polarity end through the diode in this direction through the load resistance and terminates at the negative polarity center tap point. Now as this end of the load resistance is connected to the positive polarity end, it attains a positive sign, and this end being connected to the negative center tap point attains a negative sign. So you would notice that in both during the positive and negative half cycle, the current flows through the load resistance in the same direction from the positive sign to the negative sign. It is unidirectional. So the voltage which appears across the load resistance, which we call the output voltage, has the same polarity in both the cases. So it is a DC voltage. So in this way, utilizing two diodes D1 and D2, we convert or we utilize both the half cycles of the input AC waveform into DC. In this case too, the current flows from the positive to the negative polarity end in load resistance, and in this case too, the current flows from the positive to the negative polarity end of the diode. Now another parameter which comes into play here is the peak inverse voltage. The peak inverse voltage is the maximum reverse voltage to which the entire circuit is subjected to. We know that the voltage which appears across the primary winding is equal to 2 Vm, but it divides itself equally within the center tap point OA and OB. In both the cases, the reverse voltage which appears is equal to Vm at OA and Vm at OB, as it divides itself equally. So the total peak inverse voltage, the reverse voltage which is subjected to the circuit, is equal to twice the maximum reverse voltage. So this circuit, the center tap full wave rectifier, it overcomes the disadvantages of the half wave rectifier circuit, but it too has its own share of demerits, which are, it is sometimes becomes difficult to locate the center tap point on the secondary winding of the transformer. This poses a problem. Now in this case the output is low, as each diode is subjected to only half of the voltage which appears across the primary winding. The voltage which is fed to the primary winding is 2 Vm, but what we get here? Vm only. One diode is subjected to only half of the input voltage. So consequently the efficiency is low, as half of the voltage is fed to each diode during its on state. So this is a disadvantage. So in order to overcome this disadvantage, on these two disadvantages, another modified or improved design was proposed, which is the bridge type full wave rectifier. Now this is the circuit diagram of the bridge type full wave rectifier. The same things are here. The AC supply voltage which is connected or which is fed to the primary winding of the step up or step down transformer, which is used as per the requirement. Another modified design is 4 diodes are connected in the form of a bridge back to back, which is connected across the secondary winding of the transformer. 4 diodes, D1, D2, D3 and D4. Now here the n-type ends of D1 and D2 are shorted together at A, and here the p-type ends of D3 and D4 are shorted together at B, and the A terminal is grounded while a load resistance is connected at the terminal B, or the shorted point B, across which the output is obtained. This can be also redrawn as this. Same thing, B is connected to A, in between the load resistance is connected between the points B and A, which is finally connected to ground. So in this case too, we are going to divide it or split our discussion into positive and negative half cycles response of the circuit. So during the positive half cycle, the ends P attains a positive polarity, while the end Q attains a negative polarity during the positive half cycle. So as a result, the diode D1 with its p-type end connected to the positive polarity side, and the diode D3 with its n-type end connected to the negative polarity side become forward biased. D1 and D3 are forward biased, but the opposite happens to D2 and D4, and they are reverse biased, as D4 has its n-type end connected to the positive terminal and D2 has its p-type end connected to the negative terminal. So they behave as open circuit, while D1 and D3 behave as short circuit. So the modified circuit diagram in the positive half cycle duration of the waveform is like this. This auto adjust feature of the camera is the video will come up in the. So during the, sorry for the interruption. So during the positive half cycle, the current flow takes place in this way. It starts from the positive polarity end from P, travels through the short circuited diode D1, travels through the load resistance and again through the short circuited diode D3 and finally terminates at Q, the negative polarity end. So this is you can comprehend from here. The diode D1 and D3 are forward biased and are activated, while diode D2 and D4 are open circuited. As this end of the load resistance is connected to the positive polarity end, so it attends a positive sign, while this end being connected to the negative polarity end attends a negative sign. So this is the response during the positive half cycle. During the negative half cycle, the end P becomes negative while the end Q becomes positive. As a result of this, the opposite thing happens. The p-type end of D2 being connected to the positive end Q becomes forward biased, and also the n-type end of D4 being connected to P, the n-type end connected to P, which is the negative side, becomes forward biased. So D2 and D4 are now forward biased, while D1 and D3 are reverse biased. So the current flow diagram is like this. It starts from the positive polarity end, travels through the short circuited diode D2. I have shown it here, the diode, but it's actually a short circuit. It then flows through the load resistance from the positive sign to the negative sign end, again through the short circuited diode or the forward biased diode D4, and terminates at the negative polarity, and this cycle continues. You would notice that in both the positive and negative half cycle, the current always flows from the positive sign to the negative sign of the load resistance, here and here too, the positive sign to negative sign. So it is unidirectional. So the voltage is always in the same phase. There is no inversion of the output voltage. So it is a DC voltage. So we get a DC voltage from an AC signal waveform. Now in this case, both the diodes are subjected to the same voltage, which is Vm, which appears across the primary winding. So there is no loss of voltage. So it has many advantages, this circuit, the bridge rectifier, full wave rectifier. The need for center tapping is eliminated, as there is no center tapped secondary point required. Now output is twice that of center tapped circuit, as the entire circuit is subjected to the full signal or full amplitude of the signal, which is fed to the primary winding. Now the peak inverse voltage here is Vm, which is half of that in case of the center tap full wave rectifier, which was 2 Vm. So the damage, the possibility of any damage to the circuit is also eliminated. This is the PIV, peak inverse voltage, which is half. Now other parameters which are the disadvantages, is only disadvantage is that it requires 4 diodes instead of 2, as in the center tap full wave rectifier. Now output frequency. In case of full wave rectification, the output frequency is twice that of the input signal frequency. We will see here how it happens. This is the input signal waveform consisting of both the positive and negative half cycles. Now this complete waveform completes one cycle of the signal, whereas in output it has no negative cycle. So one complete cycle is set from here to here. This is one cycle, this is another cycle. So by the time the input signal waveform completes its one cycle, the output signal waveform has already completed 2 cycles, as it converts both the positive and negative half cycles into DC output, pulsated DC output. So by the time the input signal waveform completes one cycle, it has already completed 2 cycles. One cycle of the output is said to be complete when we get a shape like this. One shape like this is equal to one cycle for output, whereas one complete shape like this is equal to one cycle of the input signal waveform, as it contains both negative and positive half cycles. But output does not contain any negative half cycles. That's why it contains only positive half cycle, and one cycle of the waveform is the positive half cycle only. Now obviously the efficiency of a full wave rectifier will be twice that of a half wave rectifier, which is equal to 81.2% or equals to 0.812. So it is obviously twice that of the half wave rectifier, or double that of the half wave rectifier. So friends, I have discussed with you some of the important concepts, basic concepts related to full wave rectification, starting from basic principle, types of full wave rectification circuits, various parameters such as the peak inverse voltage, efficiency, output frequency, related advantages and disadvantages. So I hope you like this video, and please do subscribe my channel for more such videos related to electronics engineering, and have a good day. Thank you very much.